Similarly to how Nicholas Copernicus presented the heliocentric model, another dazzling correction of how we might interpret the universe could arise, starting a discussion known as the emergence of cosmology. This emergence is set apart by critical disparities in our estimations and comprehension of the universe's crucial properties, such as its age, size, and pace of development. Neil deGrasse Tyson has noted that the discovery of the James Webb Space Telescope, JWST, has sparked this discussion with a picture that resists material science. So, what precisely is this emergency, and how does the James Webb Space Telescope contribute to it? Well, adding to it is a bit of a misrepresentation. It's more similar to a survey that has been in progress. The emergency refers to a place where how we might interpret the universe is challenged, especially concerning its age and size, which are connected by an extensive safety buffer. The presentation of the JWST has been pivotal in this setting. Before this advancement, we were limited in how far we could see into the early universe. However, with the JWST's further developed abilities, space experts can now investigate considerably more distant worlds, giving us new perspectives on the universe and testing some of our past conceptions. This advancement allows us to peer further back in time, closer to the Big Bang, and observe galaxies as they were forming. This provides critical information that can either support or challenge our current models of the universe. To understand the emergency in detail, looking into view is significant. The standard model of cosmology, known as the hot inflationary Big Bang model or lambda cold dark matter lambda CDM model, has been exceptionally successful in explaining various elements of the universe, from gravitational lensing to the structure of the cosmic web and the development of galaxies. The lambda CDM model suggests that the universe began with a Big Bang, followed by a period of rapid expansion, and has been expanding ever since. It includes components like dark matter, which applies gravitational forces, and dark energy, which drives the accelerated expansion of the universe. However, each groundbreaking observation, particularly with instruments as cutting-edge as the JWST, raises the possibility that our current model might be inadequate or need to be updated. The lambda CDM model makes explicit predictions about the attributes and behavior of galaxies at various stages of the universe's history. For example, it predicts that galaxies in the far-off past should be smaller, less evolved, and contain fewer heavy elements compared to those we see in the nearby universe. This is because heavier elements are formed in the centers of stars and distributed through processes like supernova explosions, which take time to occur. The description you give is about how the standard model of cosmology predicts the movements within groups and clusters of galaxies, as well as the properties of the cosmic microwave background, CMB. As we travel back into the past, according to this model, galaxies should be smaller, bluer, less evolved, and poorer in heavy elements at astronomical distances greater than our own. This would lead us to expect to enter times of the universe without apparent stars or galaxies. However, researchers have found contradictory evidence that challenges these expectations, resulting in an emergency in cosmology. The emergency in cosmology centers on the uncertainty about the age of the universe. Different estimation strategies give various outcomes, leading cosmologists to struggle to accommodate these disparities. To attempt to address this issue, researchers use several techniques to measure the age of the universe. One of them is the study of cosmic background radiation, which involves unraveling the history of the expansion of the universe and using mathematical models such as the Friedmann equations based on Einstein's theory of general relativity to determine the expansion rate and thus the age of the universe at different times. The CMB, a remnant radiation from the early days of the universe, is a key tool for this calculation. Detailed maps of the CMB, like those provided by the European Space Agency's Planck mission, offer important information about the composition of the universe. However, these maps lack data on dark energy, a significant component of the current universe. Despite this limitation, researchers can use the Friedmann equations along with other observations to estimate the expansion rate of the universe at different times and eventually determine its age. The Friedmann equations describe how the universe expands, accounting for the density of various components like dark matter, dark energy, and regular matter. By analyzing the CMB, researchers can deduce the conditions of the early universe and extrapolate its evolution history up to the present day. Another approach to determining the age of the universe involves observing exploding stars, specifically type Ia supernovae. These supernovae act as standard candles since they have a known intrinsic brightness. By comparing their known luminosity to their observed luminosity, astronomers can determine their distance and, therefore, the expansion rate of the universe at different times. This method, used in the 1990s, played a crucial role in the discovery of dark energy, which is now essential to cosmological calculations. It is particularly useful for determining the Hubble constant, which is a measure of the expansion rate of the universe. Although not exactly constant, the Hubble constant is instrumental in charting the expansion of the universe since the Big Bang, about 13.8 billion years ago. It has been observed that the universe has been expanding consistently. NASA has noted that the implications of this rate are significant. If the expansion is slowing down, it suggests the presence of an unknown force, perhaps dark matter, influencing this process. On the other hand, if the expansion rate is accelerating, it could indicate the presence and impact of dark energy, speeding up the universe's growth. In January 2018, researchers found something interesting. Although some telescopes showed that the expansion rate of the universe changed depending on the place of observation, the Hubble Space Telescope measured a faster expansion in the nearby universe, while the Planck telescope measured a slightly lower expansion in the more distant parts of the universe. This discrepancy in measurement highlights the vast size of the universe and reminds us of the pioneering work of Edwin Hubble, who first proposed the expansion rate of the universe in 1929. Hubble's observations of distant galaxies revealed that they are moving away from us, demonstrating that the universe is expanding. This discovery was one of the foundations of modern cosmology. Now, considering the expansion of the universe independently of your local region, you would observe the same phenomenon at the same speed as the Hubble expansion rate. Initial calculations were based on limited data. However, with technological advances such as the Hubble and Gaia telescopes, we have been able to observe more variables and refine our measurements. Different telescopes use readings of the CMB to calculate the constant, although this method has its limitations due to the availability of supernovae for distant observations, which limits our view of the universe. Since the discovery of dark energy in the 20th century, researchers have been stumped by the inconsistencies between these two approaches to the age of the universe and its expansion rate. As measurement technology becomes more accurate, smaller variations arise, driven by the development of more advanced systems. This progress, however, raises more questions than it provides definitive answers. Although the differences are minor, with just 10 to 20 million years separating the estimates, given that the universe is around 13.77 billion years old, it still warrants careful examination. One possible explanation for this discrepancy is the possibility of flaws in our measurements of the CMB. Despite being one of the most accurate measurements, it has been extensively tested since its launch in 2009 for validating its accuracy. Another perspective suggests a potential gap in our understanding of dark matter, raising the possibility that it may fluctuate over time and be linked to dark energy or some other unknown factor. This possibility has led to various experimental investigations. The accuracy of supernova measurements is also questioned, as the complexity of star explosions can introduce uncertainty into the models we use. Settling this uncertainty in supernova models could help resolve the disparity in measurements. This emergency in cosmology has been further exacerbated by the discovery of the James Webb Space Telescope. According to Neil deGrasse Tyson, the JWST found objects in the universe that challenge our current understanding. This means that our scientific understanding requires a complete update. However, the problem is that we have no idea where to begin to comprehend the extent of the scientific revolution. Let's take a look at the origins of the universe. Around 50 million years after the Big Bang, stars, black holes, and star clusters began to emerge, potentially even as soon as 50 to 100 million years later. However, these events should be relatively rare. What we don't know is how common galaxies evolved at later times, spanning events between 400 million years after the Big Bang. Ongoing JWST images reveal galaxies much more distant and, therefore, older than the standard cosmological model predicts. This disparity suggests that our model needs a major update. The discovery that the expanding universe relied on galaxies is a major development. JWST images show galaxies that formed much sooner than anticipated by current cosmological models, triggering a crisis in the field. This issue is related to galaxies and redshift, which is a common measurement in cosmology. According to the Standard Model, hydrogen began to appear 400,000 years after the Big Bang when protons and electrons combined, leading to hydrogen recombination. This changed the universe into a soup of hydrogen atoms, with some helium and residual background radiation. The gravity of the radiation then acted on small fluctuations in this hydrogen gas, slowly pulling them together to lead to the first stars. These early stars, made mostly of helium and hydrogen, engaged in nuclear fusion, creating heavier elements like carbon and nitrogen. These elements played a crucial role in galaxy formation by absorbing heat and emitting cooling photons, which facilitated the coalescence of gas into galaxies. The process of galaxy formation and evolution is complex and involves many stages. In the early universe, gas was primarily hydrogen, but as time went on, the gas became enriched with heavier elements produced in the cores of stars. This process led to the formation of galaxies that contained not just hydrogen and helium, but also carbon, oxygen, nitrogen, and other elements essential for life. The new findings from the James Webb Space Telescope, JWST, challenge fundamental assumptions about the early universe. One of the most striking discoveries is the identification of fully formed galaxies at distances that would imply they should not have existed at the time according to the standard cosmological model. These galaxies, appearing much earlier than expected, suggest that either the process of galaxy formation occurred faster than previously thought, or that galaxies formed through mechanisms not accounted for in the lambda-cold dark matter, lambda CDM, model. This discovery pushes the limits of our current understanding of cosmology and forces researchers to reevaluate theories about the timing and processes involved in galaxy formation. Furthermore, the JWST's observations suggest that the formation of galaxies may have been more chaotic and varied than the traditional models predict. While the lambda CDM model suggests a slow, steady process of galaxy growth over billions of years, the new evidence points to rapid formation and evolution in ways that cannot be easily reconciled with existing simulations. This discrepancy has profound implications for our understanding of how galaxies evolve and how stars, black holes, and other celestial objects are born within them. One of the most significant implications of these findings is that the early universe may have been far more dynamic than previously thought. The JWST's ability to peer into the most distant corners of the cosmos allows us to observe the earliest stages of galaxy formation, which could include the formation of large structures such as black holes and stars that would not have been expected so early. This raises questions about the timescales involved in these processes and whether our understanding of how galaxies and stars are created is fundamentally flawed. Another challenge posed by these new discoveries is the possibility that dark matter and dark energy behave differently than our models predict. While dark matter has been theorized to play a key role in the formation of galaxies by providing gravitational pull, the detailed mechanics of its interactions remain unclear. The new data from the JWST may suggest that dark matter's properties or its role in cosmic evolution need to be reconsidered, adding to the ongoing mystery surrounding its true nature. In addition to these challenges, the discovery of galaxies and other cosmic structures that defy the predictions of the lambda CDM model may force cosmologists to rethink the basic principles of cosmic inflation. This theory, which suggests that the universe underwent an exponential expansion in the first fraction of a second after the Big Bang, has been one of the cornerstones of modern cosmology. However, the observations made by the JWST could indicate that inflation occurred in a way or at a time that we previously did not anticipate, requiring a new framework for understanding the universe's early moments. As the field of cosmology grapples with these new revelations, it is clear that the current understanding of the universe's formation and evolution is in flux. The implications of these findings are far-reaching, potentially necessitating a revision of not just models of galaxy formation but also our fundamental understanding of the forces shaping the universe. This emergent cosmological crisis highlights the need for ongoing observation, analysis, and theory building to refine our understanding of the cosmos and our place within it. The discoveries made by the James Webb Space Telescope have sparked a crucial reevaluation of many cosmological theories. The newly identified galaxies that formed much earlier than previously predicted challenge the established timelines of cosmic evolution. This raises critical questions about the processes that govern galaxy formation and the role of various cosmic elements in shaping them. If galaxies existed at such early stages, what mechanisms enabled this rapid evolution? And what does this tell us about the conditions of the universe in its infancy? Moreover, these revelations may lead to more sophisticated models that integrate new forms of cosmic phenomena. Understanding the early formation of galaxies could reveal new insights into the formation of supermassive black holes and the interaction between dark matter and ordinary matter. The JWST has also provided evidence that many of the structures we observe in the universe may have been shaped by forces or events that we currently don't fully understand, urging scientists to consider new theoretical frameworks that go beyond the scope of current cosmology. As we probe deeper into the universe's history, there's also the challenge of reconciling these findings with observations of the cosmic microwave background and other large-scale structures. The clash between the new data and the long-established models signifies an exciting time in cosmology, where existing paradigms may be on the verge of significant transformation.